Okay, let's dive into something really quite mind-bending today. The James Webb Space Telescope, JWST, right? It's been completely revolutionary, giving us this view back, way back in time.
Absolutely. We're talking about the cosmic dawn.
Yeah, that window, what is it, maybe 50 million to a billion years after the Big Bang?
Right around then,
Yeah.
when the very first stars, the first galaxies were just, well, just starting to appear.
It's like getting the universe's baby pictures.
Exactly. But, while Webb's giving us these amazing pictures, it's also throwing up some real surprises, things that don't quite fit.
Like what specifically?
Well, we're seeing lots of these little red dots. They look like unusually bright, very compact galaxies. And maybe even more startling, we're seeing signs that the seeds, the very earliest seeds of supermassive black holes.
Okay, right. And that's where things get tricky for our standard understanding, isn't it?
It really is.
Because these findings, they just don't seem to line up with our models for how galaxies are supposed to grow and evolve over time.
Precisely. We're finding these incredibly massive objects, these supermassive black holes, way earlier in the universe's history than we thought possible.
It really poses a major cosmic riddle.
It absolutely does. I mean, our standard cosmological picture, lambda cold dark matter, or CDM for short,
Right.
it predicts this long period after the Big Bang called the cosmic dark age. Basically, the universe was full of neutral hydrogen gas, soaking up most light.
Only the cosmic microwave background light, and then much later, the very first stars were supposed to light things up.
Yeah, those population 3 stars. The first generation. Giants made of just hydrogen and helium, basically. Nothing like stars today.
And they were supposed to be the ones that gradually reionized all that hydrogen gas, making the universe transparent. The epoch of reionization.
Exactly. But the black holes Webb is spotting now seem, well, far too big, too massive, to have grown according to that TDM timeline.
So it makes you ask, are we missing something fundamental? Could there be like a whole chapter of cosmic history we just didn't know about?
That's the core question.
So, okay, that's the big puzzle we're going to try and unpack today. We'll dig into how astrophysicists are basically having to rethink how black holes form right at the beginning, and what these Webb discoveries really mean for our picture of the universe's first light.
Yeah. For a long time, the discussion about how these early supermassive black holes got so big so fast, it sort of revolved around two main possibilities.
Okay.
The first one, people often call it the stellar collapse model. The idea was that supermassive black holes grew from smaller ones, the kind that would form when those first huge POP3 stars died and collapsed.
So starting small and growing over time, a seed growing into a giant.
Pretty much, a growth from seed idea.
And the other option.
The other was the direct collapse model.
Uh-huh.
This one suggested maybe they skipped the star part altogether, that these supermassive black holes could form straight from enormous, dense clouds of pristine gas collapsing in on themselves. No star needed first.
Just poof, a black hole.
Sort of, yeah. Straight from gas to black hole.
Okay.
Now, there's a really bold new idea called the POP 3.1 model. It's adding a lot of weight to that direct collapse idea, but with a twist. It's from astrophysicist Jonathan Tan and his group. Sure. And it's pretty revolutionary.
POP 3.1. Okay, let's break that down. What's Tan's theory saying?
So his idea, which they published recently, suggests that truly supermassive stars, not just big ones, but maybe hundreds of thousands of times the mass of our sun, formed directly from that primordial hydrogen gas. But here's the twist, or the kicker, as you said earlier. These stars would have been incredibly luminous. So incredibly bright, they would have rapidly ionized everything around them, like a brilliant but very, very short-lived cosmic flash.
So it's still a direct collapse, but into a supermassive star first, which then collapses into the black hole seed.
Exactly. It's a slightly different pathway, but it gets you to that massive seed very quickly.
Huh. So what does that imply for the early universe?
Well, it means the universe might have had two completely separate bursts of light and star formation. First, this very brief, super intense flash from these POP 3.1 supermassive stars. Their collapse then seeds those early supermassive black holes Webb is finding.
Okay, flash one. Then what?
Then, after that initial flash died down, you get the second wave, a more, let's say, normal and sustained period of star formation, the kind of stars and forming galaxies that Webb is looking at now, deep in the cosmic dawn.
So, hang on. Are you saying what Webb is seeing, those distant galaxies we thought were the very first light, might actually be the universe's second attempt, like Act Two.
That's the mind-bending implication, yes. What we're seeing might not be the absolute dawn, but more like the dawn after a brief earlier dawn.
Wow. Okay, that changes things.
It really does.
Yeah.
And when you think about the bigger picture, Tan's model doesn't just solve the how did black holes get so big so fast problem. What's really exciting is how it potentially connects to other major puzzles in cosmology.
That's what.
Well, think about it. If these pop 3.1 stars reionize the cosmos much, much earlier than we previously thought.
It changes when light could travel freely through the universe.
Exactly. And that earlier reionization date could subtly change how we calculate the universe's expansion rate over cosmic time.
Which could potentially help with the Hubble tension, that nagging disagreement.
That's the hope. The Hubble tension is this mismatch between how fast we measure the universe expanding nearby versus what our models predict based on the early universe's signals like the cosmic microwave background.
Right.
An earlier reionization, as predicted by the POP 3.1 model, could tweak those early universe calculations just enough to potentially ease that tension. It's like a ripple effect.
So this isn't just some obscure detail about black holes. It could actually be pointing towards a modification of our whole cosmological framework. That's huge.
It is potentially huge.
Could it even hint at, I don't know, wilder ideas, like maybe dark energy isn't constant? Or even stranger things about fundamental particles, like neutrinos maybe having negative mass? That sounds very speculative.
It is speculative at this stage, absolutely. But yes, tweaking the early universe history could open doors to exploring possibilities like dynamic dark energy or these more exotic particle physics ideas. If POP 3.1 stars really did ionize the cosmos earlier, they rewrite the history of that epoch of reionization. And that rewrite could potentially relieve several different tensions that have been building within the standard CDM model. It's quite elegant, potentially solving multiple problems at once.
And we've had clues about these direct collapse black holes before, haven't we? I remember hearing about finding these incredibly bright quasars.
Yes, exactly. Quasars are basically supermassive black holes actively feeding on gas, shining incredibly brightly. And we found some dating back to only maybe 500 million years or so after the Big Bang, which is already hard to explain.
But now with Webb, we're not just seeing the bright quasars later on, we're potentially seeing the actual seeds themselves much earlier.
That's the key difference. Webb seems to be giving us a direct view of those primordial seas, or at least the galaxies hosting them. It moves from theoretical possibility towards something potentially observable.
Richard Ellis, he's a well-known cosmologist, right? What does he make of this?
Yeah, Richard Ellis at University College London. He described Tan's work as an elegant model. He pointed out it could explain this sort of two-stage process for stars and ionization early on. He also noted it's entirely plausible that the very first stars shone brilliantly for a short time and then, poof, they were gone.
Which really supports this idea that Webb won't be seeing Act Two.
It does. It reinforces that idea.
Yeah.
The universe, well, it clearly still has some big surprises up its sleeve.
Okay, so let's try and wrap our heads around this. This new POP 3.1 model, it gives us a pretty compelling story to make sense of Webb's findings, these surprisingly big black holes so early on.
Right. It suggests maybe the universe lit up twice. An early, brief flash seeding the black holes, followed by the longer dawn that Webb is now probing.
So what we see as the first light might actually be the second light.
Essentially, yes. A second act in cosmic history.
And the ripples go way beyond just black holes. It could help with the Hubble tension.
Potentially, yes. And it might even open the door to thinking about dynamic dark energy, or even stranger things like negative neutrino masses, though that's still very much out there.
It really makes you think, doesn't it? About this possible hidden chapter right at the start of everything. If supermassive black holes were shaping the cosmos in this unexpected way right from the get-go, how much of the universe we see today, the galaxies, the large-scale structure, is actually a legacy of those very first moments, those first stars and black holes.
Exactly. Did the universe kick off with this incredibly important but hidden phase that we're only just now starting to piece together because of instruments like Webb?
It kind of suggests that figuring out where black holes came from isn't just, an interesting astrophysics problem.
It might be more profound. It could actually be, as some suggest, a doorway to a completely new cosmology, a whole new way of understanding the universe's origins and evolution.
Leaves you with a sense of awe, really. Still so much mystery out there.